Homework 1.4, section complex numbers. Video number 1, homework due May 16th, 2020. Welcome to the first series of lecture videos for college algebra for the Maymester 2020 term at Tyler Junior College. My name is Chris Chaplin, and I'll be happy to teach you some math. At the beginning of each video, I will start by announcing the homework number and the section title, the video number in the series for this homework, and the due date for whichever assignment we're currently covering. Also, I'll title each individual video with something specific, like types of numbers part 1. I don't know how many videos I'll have in each series for each homework assignment. I try to keep them between 5 and 10 minutes each because I know that it's hard for most people to watch a 50-minute math video. So I'd rather give you a bunch of shorter videos that you can watch and digest individually. Also, during or at the end of some of these videos, I will say now would be a good time to stop, go into the homework, and look at these particular questions. This way, you don't have to just watch an hour worth of videos and then try to do your homework. You can watch a little bit, try some homework. Watch a little bit, try some homework. And my plan is to do this for every single topic and every single homework assignment that we do in this class. All right, so let's go ahead and start this video. This content is types of numbers. This will be the first part because I plan on splitting this into 2 videos so that I can keep them relatively short. But before we get into actual complex numbers, I want to briefly review some types of numbers that you've seen before and remind you what they're called, because throughout this course I will say things like this has to be an integer or this has to be a rational number, and I'm going to kind of expect you to remember what that means. So let's start with the first types of numbers that most people encounter. They're called counting numbers because those are the numbers that you count with. So ask any little kid that's learning how to count, can you count for me? And they'll probably start with 1, 2, 3, etc. Now most of the time when you have a set of numbers, they're included in a pair of braces, which look like parentheses that somebody pinched. And I think most of you know that 3 dots in a list like this imply that this list continues as the pattern is set forth. So 1, 2, 3, 4, 5, 6, etc., etc. These 3 dots are called ellipses. I'm also going to allude to some of the historical development of some of these numbers, sets of numbers, without getting into too much detail. One thing that led to the development of more and more intricate number systems is the need for such a system. Not necessarily from an applied or real-world perspective, although all of these do have real-world applications, but also from a theoretical perspective. For example, as numbers were being developed, so were things like algebra. So if we create a problem using counting numbers like x plus 2 is equal to 5, I'm assuming that you know how to solve this. There are some basic algebra skills you're expected to know coming into this class. I'm assuming all of you know that one way to solve this is to subtract 2 from both sides and get x equals 3. So what this is an example of is an equation that was made using counting numbers, and its solution is also a counting number. But we're going to run into a problem because there are equations that we can build with counting numbers who don't have a solution. For example, if I give you something as simple as x plus 2 is equal to 2, we can all solve that. You can probably look at it and tell me what the solution is. But if the only numbers you know are these, it has no solution. We know the answer is 0, but if you only know counting numbers, there is no 0. So there's this cat and mouse game that was played in the development of math. We've got numbers, we've got equations. Can we solve every equation? If the answer is no, it means one of 2 things. We've reached the end of the numbers we're going to use, or there are more numbers we just haven't found yet. Now, we know that this is equal to 0, and from a historical perspective, it took quite a while for the idea of 0 to actually gain some ground. Why should we have a number that represents nothing? Well, because if I give you this on your test and say, oops, I'm sorry, it was this, but it's only a 0, yeah, that 0 makes a difference. So, the next set of numbers that was developed is called the whole numbers, which are just the counting numbers, but it includes the number 0. 0, 1, 2, 3. And everything was okay for a while, until the theoretical guys, the theoretical mathematicians, who were doing math for the sake of doing math, and believe it or not, it's a nice endeavor. We're fiddling around with problems like this and said, well, can I make an equation using only whole numbers that doesn't have a solution? And so somebody posed a problem like this: x plus 5 is equal to 2. If the only numbers that you know are whole numbers, this has no solution. It's like asking a first grader, what can you add to 5 to get 2? They'll probably tell you you can't, because when you add to 5, it's going to get bigger or stay the same if we add 0. Now we know the solution, and we know how to get there, subtract 5 from both sides. But again, if whole numbers are the only numbers you're working with, this has no solution. So either we hit the end of math, or we need more numbers. And of course, we get more numbers. The solution of this equation is -3, which means we need negative numbers. In come the integers. The integers are just the positive and negative whole numbers and the number 0. Now, because negative numbers go to the left, so to speak, and they go forever, I have to start this set with ellipses, and then just pick it up, we'll say with -3, -2, -1, 0, 1, 2, 3. I really don't need to go that far. I just wanted to show that we are adding on to the set of numbers that we already have. We have the whole numbers, and now we picked up the negatives, and now we have what are called the integers. And everything's okay for a while. But what type of equation could we create using integers that doesn't have a solution that's an integer? I'll give you a hint. It can't involve addition or subtraction. With the integers, if you add or subtract, you will always get another integer. So there's no way we could come up with an equation with no solution if we only use integers with addition and subtraction. But what about multiplication and division? If we had something like 2x equals 6, 2 times x equals 6, I think most of you know, or rather most of you should know, that the move to solve this, or a move to solve this, is to divide both sides by 2, which would give us x equals 3. Look, we made an equation with integers, and the solution is an integer. But can you think of an equation with integers whose solution isn't? How about instead of 2x equals 6, about 2x equals 5? There's no integer that when you double you'll get 5, but does that mean this has no solution? Of course not. If we divide by 2, or try to divide by 2, we get a new type of number. And this is where most people start running away from math, hands in the air screaming like they're trying to get them. Oh no, it's a fraction. I'll tell you right now, we are going to run into fractions, and I fully believe that you can handle it. You may have this mental block that I don't know how to do fractions. Yeah, you do. And I'll remind you how to do them when the time is right, whether it's adding, subtracting, multiplying, dividing, or solving equations with them. But it's all about perspective, about how you see fractions, and it's all about, it's just what you think about them. Honestly, they're not really that bad. You just have to stay focused. But I digress. So with this type of equation, we pick up a new type of number, most commonly known as fractions, but technically they're called rational numbers. The reason they're called rational numbers is because each fraction is a ratio of integers. So basically, rational numbers are just pick 2 of these and put one on top of the other, with one exception. Never let a denominator equal 0. Everything just goes to pot when you let the denominator equal 0. So in come the fractions, in come the rational numbers. But now we run into a problem on how to write them. Up until now, I could just list them in a row and maybe go forever on one side or the other, or both, and everything was okay. But the problem with rational numbers, with fractions, is that they are so densely packed, I can't just list them in a row. For example, consider 0 and 1. If we were only dealing with integers, there's no more numbers in between here. But the minute we start allowing fractions and decimals, how many fractions are there between 0 and 1? The answer? An infinite number of them. In fact, they're so tightly packed in there that no matter what 2 fractions you give me, I can always find one in between. For example, 1/3 is between 0 and 1. So is 1/2. 1/3 is less than 1/2, so we'll write it to the left of it. Can you find another fraction in between? I don't think so, but you can, because you can always get a common denominator like 6. This would be 2 over 6. This would be 3 over 6. and it looks like we still can't fit something in between, but if we doubled everything, you can unreduce fractions. If we multiplied both sides of this by 2, we would get 4 over 12. If we multiplied both sides of this by 2, we would get 6 over 12. And now I think I can fit 5 over 12 in between them. But we can always make the fractions have larger numerators and denominators, which means we can make a bigger gap between the numerators, which means we can always fit more numbers in there. Basically what that means is rational numbers are so densely packed, you can't just list them in a row. No matter what two you put next to each other, you can always fit a bunch more in between. So we can't just list them anymore. So what do? We describe them. To describe the rational numbers, I have to say what I would do to build one. Well, I would make a fraction and put one number on top. I'm going to put n for the numerator and one number on the bottom. I'll put a d for the denominator. And then I have to say where those numbers come from. Now, I'm doing something called set builder notation. Don't worry about it for now. But this vertical line basically translates into the phrase such that. So I want the set of things that look like this such that n and d are integers, and the stipulation that the denominator is not 0. So again, it's an attempt to describe all the fractions instead of list them all. Now, you might think that's all the numbers. Let me step over here and see how long this video is going. I may pause and start part 2 sooner than I thought. Yeah, we've already passed the 10-minute mark, and although that's going to happen from time to time, because I'm going to do this topic in 2 parts, I'm going to go ahead and pause this now, and then we'll pick up with real numbers and then transition into complex numbers up there into the next video. There we go.